This class is designed to help the student of class 10 who are going to appear SEE examination. Today's class is related to the chapter force, and today I am going to focus on the derivation of force. I mean to say there are two important derivation given in the chapter force, and we are going to learn about those two derivations. What are they? Look at this. Number one is F equal to G m1 m2 by d square. We are going to derive this equation. And second is another expression, G is inversely proportional to the square of the radius of the earth. Okay, let's start with the first one. If you are told to prove F equal to G m1 m2 by d square, first we have to understand the meaning of this symbol. For this, I am going to write something. Look at this. Let's say this is a body. This is another one. The mass of this body is, let's say, m1. Mass of the second body is m2. And they are separated by a distance d. m1 first mass, m2 second mass, they are separated by a distance d. Look at this. Let m1 and m2 are two bodies separated by a distance d. Then how much gravitational force between them produces? We are going to prove that. For this, first we have to mention Newton's law of gravitation. According to Newton's law of gravitation, the gravitational force between any two bodies is directly proportional to the product of their masses and inversely proportional to the square of the distance between their centers. What is the meaning of this? We are going to find out the meaning of this law comparing with this situation. According to this law, gravitational force F is directly proportional to the product of the masses m1, m2. Look at this. And this is, let's say, equation 1. Again, what is told? The gravitational force between two bodies directly proportional to, that's why I do this, to the product of their masses, that's why I am taking m1, m2, and inversely proportional to the square of the distance between their center. The same force F is inversely proportional to the square of the distance between their centers. This is equation number 2. Combining equation 1 and 2, what we get? F is directly proportional to m1, m2, and the same F is inversely proportional to d square. It means F is directly proportional to m1, m2, but inversely proportional to d square. It means if any quantities are proportional to each other, then there must be a constant. That's why this proportion sign can be converted into equal to sign, but what constant inverse between them should be written in the expression. The constant between them is taken as gravitational constant. It is denoted by capital G m1 m2 by d square. That's why what can we conclude? The gravitational force F is equal to G m1 m2 by d square, where G is gravitational constant. This way we can prove that F equal to G m1 m2 by d square. One derivation completed. Now I want to derive second one. Look at this. Prove G is inversely proportional to the square of the radius of the earth. The meaning is, if radius of the earth is more at a place, G will be less. If radius at a place of the earth is less, then G will be more. Now for this we are going to consider something. Look at this is, let's say, mass of earth. It is taken as capital M. And a body is lying on its surface. Let's say its mass is small m. And this is the radius of the earth, R. Now we can consider all this symbol here. Capital M, mass of the earth. Small m, mass of a body lying on the surface of the earth. Capital R is the radius of the earth. And G is acceleration due to gravity. Capital G is gravitational constant. Now considering all this symbol, now we have to go through derivation. According to Newton's law of gravitation, just now I found this. F equal to G m1 m2 by d square by derivation. Now, according to this Newton's law of gravitation, gravitational force F is equal to G. In place of writing m1, I am writing capital M, because in this case first mass is the mass of the earth, and in place of writing m2, I am writing small m because the mass of second body is small m, and the distance between these two is the radius of the earth. That's why instead of writing d square, I am writing r square, and this is same as this equation. That's why I can consider this as equation number 1. Now, according to Newton's second law of motion, do you remember Newton's second law of motion taught in class 9? What was the conclusion? What was the equation related to Newton's second law of motion? F is equal to mg. F equal to mg. But at that time you are told not g, F equal to ma. If this force is not the applied force, if this force is the force applied by the earth, then the acceleration will be acceleration due to gravity. That's why we are writing F equal to mg. Now this is considered as second equation. Now we have two equations. First one, F equal to G mm by r square. Second, F equal to G, F equal to mg. Now combining equation 1 and 2, what we get? If F is equal to this, F is equal to this, then mg is equal to capital G, capital M, small m by r square. Mm cancel. Now what is left behind? Or G is equal to capital G, capital M by r square. Looking at this equation, it's clear that acceleration due to gravity depends on 3 factors. What are they? Gravitational constant, mass of the earth, and radius of the earth. But really, it doesn't depend upon these 2 factors, capital G and capital M. Because I want to give you example. Let's say this is earth. Actually, earth is flattened at the pole and bulged at the equator. This is earth, and this is north pole. Let's say if a body is dropped at north pole, the acceleration due to gravity is found 9.83 meter per second square at north pole. And if the same body is dropped at equator at this place, then acceleration due to gravity small g is found as 9.78 meter per second square. Look at this value. Acceleration due to gravity is more at pole, less at equator. Now, I want to come back to this equation. This acceleration due to gravity is more at pole, but less at equator. But in these 2 cases, capital G remains same. It means this G doesn't depend upon capital G. But when a body is dropped at pole, we found this much is the acceleration due to gravity. When the same is dropped at equator, this is the acceleration due to gravity. But when it is dropped at pole, mass of the earth is more. Or when it is dropped at equator, mass of the earth is less. Is this correct? This is wrong. Mass remains same whether a body is dropped at pole or whether it is dropped at equator. It doesn't make any difference. Then why should we consider this as a factor which alters the value of small g? This is wrong. That's why what can we say? G doesn't depend upon capital G and capital M because they are constant whether a body is dropped at pole or equator, their value remains same, and that's why the value of G doesn't depend upon these two quantity. That's why here capital G and capital M are constant. Therefore, G is inversely proportional to R square. If we remove this constant, then equal to sign also removed and proportional sign is taken. G is inversely proportional to R square. This way we can prove it. And for your convenience, you can get all this in this book. There's Enjoy Science. I wrote this book. Including this, there are many things. If you want to know other matter related to this derivation, you can get it. This much for today. We will meet in another class.